some bad news for you. Start with the bad news. I'm new with this. I'm inheriting this from a former, well, current colleague of mine, but he decided he didn't want to make the commute from Burlington, Vermont anymore. Can't blame him. Yeah, exactly. So, the good news is I am a PE, so I have passed not too long ago, in 2013. This and the PTOE. So, what I lack in presentation, hopefully I'll make up the speed and try and cover as much material as possible. With an eye toward problem solving more than cram course in traffic engineering. Show of hands, how many are traffic engineers or planning to be? You're on the fence. Okay.
Transportation.
Transportation.
General.
Good, okay. All right, so you'll benefit from the depth, and everybody else, yeah, you might be able to pick off some low-hanging fruit. So we'll go for it. Now I guess I better get mic'd up here.
You can put it in your pocket.
All right. I don't have pants pocket, I guess.
No, yeah, you can put it here.
I'll take my phone out. Apparently we're going on YouTube. I just want to make sure that this is do not disturb. Okay, what's next? Anywhere in here is fine, I assume?
Yeah, that's
Is that good?
all set.
Okay. Wow. Let's throw that back there and get that out of the way. We'll get this. All right.
We picked this up on YouTube?
You know, I do. This is the first I'm hearing about this. If I had my choice, I'd say, give me warning next time I'm going to be on camera.
If we missed the class, will we see this somewhere?
He doesn't. I don't know, and he doesn't know who's calling for this to be recorded. So we don't know if it's BSCES or some entity within the university. If I get information on that, I'll share it with you when I share you my notes.
We missed it.
Huh?
It'd be nice to know if we missed the class.
Yeah, well, I would have thought that BSCES would have mentioned that up front if that was the case. So you can very much follow up with them. So let's get some of the, credentials. You get to see my whole setup here. Exam, PE refresher, 2019 fall. Let's find out who's here. All right, if you see anything, particularly with regard to the email that's not right, let me know and I'll amend it. I'll start right here. Who do we have? Mr. Maxwell is here.
Cahoon.
Mr. Cahoon is here. Right off the top. Sir.
Brendan O'Brien.
Brendan, welcome. Okay, back row. Sir. Fernando. Oh, Hishan Fernando. Got it. Or is it the other way around? Which is your given name?
Hishan.
Hishan. Okay. Sir.
Dave Sacco.
All right. Sir.
Rob Truex.
Benjamin Rollins.
Benjamin Rollins. Oh, okay. And these are my, yeah. Neither of you are Nick or Just. I'm Just A. All right. If they make it, they make it. So I'm assuming everybody's happy with their email. Is there a way to dim the light that's right on the screen? Yeah. Why don't we try playing with those? Because I don't want to take away from your viewing experience. Excellent. Thank you. I'm going to cheat this way. All right. Save that. And we'll kill it. All right. Let's go up a level. Let's get to the notes. let's go up a page. 2 pages. All right, if you haven't seen this, this is the specs for the exam you'll soon be taking. And I've highlighted what I'll be covering tonight as it regards traffic engineering. I'm doing the traffic side of transportation, and Peter Reed, I believe, is handling the highway aspects of transportation. So after tonight's course, I'll share with you my notes, so you'll have them for reference. All right, so the 2 areas that I'm covering with respect to traffic volumes and safety, as they're outlined here in the breadth, I'm going to basically, you'll pick up of those through the depth that we're going to cover today. So traffic volume, safety elements, they're analogous to Section 1I, highway safety, and volumes you'll just pick up as you go along through some of the other subheadings, traffic analysis primarily. So I'm going to cover as much depth as I can, and those of you who are interested in it only from a breadth perspective, well, you get a bonus. All right, let's see. I'm going to get the notes up here. All right, so having inherited these, I came to find out that I don't have quite everything covered here. Street segment interrupted flow, but elements of that you'll be able to glean from discussions of uninterrupted flow. And traffic forecast, for the life of me, I don't remember seeing that on either exam, either the PE or the PTOE, so you're not missing much by not having that. I'm assuming those of you who may be doing it for depth will have a study guide, much like this one, Transportation Depth, 6-minute problems. There you could probably find what you need in terms of traffic forecast, if you're so inclined. All right, so I am going to veer slightly differently from this line up here. I'm going to add a couple of windows here so we have some references, and allows me to jump back and forth. New window, and just let me get myself organized here, and we'll get rolling. For posterity and for the recording, my name is Jack Martin. I'm a traffic engineer with the firm Stantec in Burlington. I've been a PE since 2013. I've been a PTOE since 2013. I knocked them both off in the same year. I figured, what the hell? I know all this. I've done all this prep. Keep on going. All right, let me just get this down and pull it on side. Okay, so now I have some references. Despite the order you see there, I'm going to jump a little bit. I'd like to start low and slow with just some traffic analysis terms. All right. Pull this over so I can expand it a little. All right, let's just start with some basic terminology. Average daily traffic. You'll notice when you come down Route 93, you'll be passing over, probably in Stoneham, you'll pass over some inductive loops in the road that count cars as they go by, and then they count how many cars go by in a day, and then over the course of the year, they'll average them out, and you'll get a average daily traffic. I think on 93, it's anywhere in the neighborhood of 150,000 to 200,000. Good evening. Welcome. Can I get your name quick so I can check you off? Can I get your name?
Nick.
Nick. Welcome, Nick. I'll try to remember that later when I fill you in the attendance sheet. We're just starting low and slow with some background traffic terms, and then I'll go into some example problems. So average daily traffic, pretty much as you imagine on a given roadway, any number of vehicles per day that pass the point. As I say, data collected often using an ATR. And what is an ATR, you ask? ATR, automatic traffic recorder. As it says, typically pneumatic hose. On 93, they're inductive loops. Stretch across roadway, embedded, so it's connected to a traffic counter. Permanent installations are often used to measure seasonal variations. Design hour volume represents the design standard for the roadway. Roadways are designed to carry the design hour traffic volume at a given level of service. So the 30th highest hourly volume recorded in a year is often used as the design hour volume. Permanent count station data, again, is often used to collect hourly data. I'll have to edit that. There is no, as yet. See following figure. K factor. K represents the percentage of daily traffic volume occurring during the peak hour or design hour. Rule of thumb, 9%. K factor in a peak hour. So when you see it in like a MassDOT plan, you'll see the K is given as 9. Understand that that's a percent when you do calculations. Similarly, the D factor, directional factor. Roads have directionality. 93 south, heavy in the morning southbound, heavy in the northbound in the evening. So the D factor is a representation of the split. Oop, wow, that's very grippy. Sorry about that. I'll just come back there, okay. T factor, trucks. Often in analysis programs, the default is 2%, but that, again, you can measure it through ATRs, the way they set the tubes, the span of the depth between wheels on a trailer will tell you if a truck is compared to a car. Turning movement count. And more of this is being done with cameras these days, but if you've ever seen somebody sitting by an intersection with a board and pushing buttons, they're counting turning movements, things that you really, well, until video capture came along, things you really couldn't capture with just turning with tubes. You would need to see vehicles turning left through right, and somebody would count them typically in a peak hour, and then you would use these numbers for your analysis of intersection capacity. So turning movement counts. And you can count, typically we count cars, but as we've gone more multimodal, trucks, PEDs, bikes, they can also be counted. Peak hour factor, a measurement of how much, it's the relation between a peak 15-minute period, which is often intervals used for analysis, as compared to the full hour. So the peak hour factor is a way to convert. Hey, there's our full house. Just A, or how would you pronounce that? Just? Yes. Welcome. Okay, everybody's here. All right. So peak hour factor, it's always less than one. Well, let's put it this way. If the peak 15 minutes were the same throughout the hour, your peak hour factor would be 1. But since the peak 15 minutes an hour is always going to be more than the other 3 15-minute periods, you're going to end up with a peak hour factor that's less than 1. It's going to range typically from 0.75 to 0.95. If you lack hard data in terms of count data, a default value is commonly 0.92. So let's get into it with just calculating a peak hour factor here.
this example problem here. Determine the peak hour factor for the reported traffic data given these 15-minute traffic volumes. So what you need to calculate your peak hour factor, you need to know the peak 15 minutes, you need to know the peak hour. So let's see if I can get in here. Zoom. All right, so we've got this traffic data. It was a PM peak hour collection from 4 to 6. Normally this will be done for you, of course, with the software, but you should know what goes into it. So we need to sum the various hour-long periods, and then we'll find the peak 60-minute period among them. So I'm just going to do some quick math. 3, 1, 12, 13. So it's 26, 35 there. And then, so that's the period from 4 to 5. Then the period, so say from 4:15 to 5:15, we would go with these 4. So that is 5. 5, 10 is 5. 11, 26, 27. And then we go to the next block. So another way to look at it, if we go 625 and we drop down to 600, we're losing 25 vehicles. So this is going to go to 2730. Come on. Can't stop or else it's going to group them all together. 2730. And my math checks there. And then the next hour-long period, we drop 530, but we only pick up 510, so we're losing 20 more. So that goes to 2710. Go up there. Getaway. 2710. And last but not least, the last 15-minute period still declining. We're losing 880, and we're only picking up 500, so minus 380 is 2330. So by inspection, here is this 2755 is our peak 60-minute period, which is those 15 minutes, those 4 15-minute periods. And the peak 15-minute period is the 880. So our peak hour factor, the volume for 60 minutes over 4 times the volume. I'm just gonna, sorry about this, still getting used to the new, there it is, that's what I want. All right, so we got 2755 over 4 times 880. Who's got a calc for me? 2755 over 3520.
0.78.
0.78. All right. So now you can speak intelligently about peak hour factors. All right, let's talk about vehicle speed data that's commonly recorded to some typical uses for those. Law enforcement. Well, let's start in order here. You want to set your speed limit. So speed limits are typically set on the 85th percentile of vehicles traveling through on a roadway. That's where your law enforcement will come in. You want to set the design criteria for a roadway, for instance, or if you need to, when you do a design exception report, if you're looking for a design exception, you've got to document the speed, and you may need to do it as it may have been posted and measured at one time, but conditions may have changed that the speed varies from the original posting, and you want to document the speeds. So how do we go about determining these things? Mean speed, that's pretty straightforward. It's an average. Median speed would be the 50th percentile. Half the measurements are below the median speed, half the measurements are above it. 85th percentile, what is the speed at which 85% of the traffic, 85% of the vehicles are going at that speed or lower? Equivalent to your design standard. Mode, most frequently observed speed. So if you imagine a curve, sort of a histogram, the mode would be the largest area under that curve, most recordings. Pace is finding the 10 mile per hour speed range that has the most observations. So, all right. So let's take an example here. Given so when they measure this out in the field, they'll record cars going over tubes, and the rate at which the cars go over the tubes tell you how fast they're going. So you get a report back saying think of these as boxes of speed ranges. What would be the speeds we're looking for? The mean speed, median speed, 85th percentile, particularly important information. So you got these speeds and these frequencies. Let's crunch some numbers really quickly. When you're looking at a average speed is basically it's a weighted average. So you're going to look at all these speed groups, and you typically so you would multiply the speed by the frequency, and then sum those up, and then divide by the number of instances you have to get your average speed. So if we do a quick check here for 25, as a matter of fact, I'm going to do a running total here. So we got 1 plus 3 is 4, plus 21 is 25, plus 41 is 66. And this will come in handy in a moment. You'll see why. Plus 38 is 104. Plus 10 is 114. Plus 4 is 118. And 2 is 120. So we've got 120 observations at these various speeds. So to get our weighted average, we want to multiply, don't do that, 120. All right, so we're going to assume a speed for each range. And you just pick the middle speed of the range. So we got 13, go away. So 11 to 15, middle speed is 13. Why are you doing this to me? 13. 16 to 20. I must be leaning on something. And I'm going to delete you. All right, so I'm going to go right through these. 13, 18, and as you can imagine, it goes up by 5s. 23, you'll be happy to know that these are also summarized in the notes, but I want to take you through the process of looking at the data and working out the problem, and then you can go back and review it afterwards. We got 28. Oh man, I knew this was going to be my downfall, which is also why I didn't want to be recorded tonight, but I don't have any choice in that matter. 28, 33, I'm just going to go right down the line, 38, 43, and 48. All right, so let's slide that over. All right, so to get our weighted average, you multiply the speed by the number of observances, this frequency table here. So 13, 18 by 3 is 54, 21 by 23, you know what, I'm just going to cut to the chase because I have that information. So you don't have to watch me do my math in my head. So 483, 41 times 28, 1148. 33 times 38, 1254. Because unfortunately, this is what you'd have to do in the test. You've got to work all this out on paper. 10 by 38, 380. 4 by 43, 172. And 2 by 48, 96. And lo and behold, that all adds up to 3,600. Smart of them to figure that out. So our mean speed, the average. Come on. No, you can do this. Oh, there you are. You're up there. Average, 3,600. Total over a number of observances, 120, 30 mph. All right. Our median speed, what's the break point? Half of them above and half of them below. Well, we got 120 observances, so the halfway point would be 60. So where does that 60th observance fall in? It falls in this group of 41 observances, which is the 26 to 30 range, which we've assumed to be 28. So your median speed, 28 miles per hour. Similar approach, what's the break point between 85th percentile? 85% of 120 is 102. So where does that 102 come in? Let's see, we've got in this group of 38, we go from 66 to 104, so the 102nd person is in that group. And so that is in the group 31 to 35, which we have assumed is 33 miles per hour. So your 85th percentile is 35 mph, 33 mph. The mode frequently observed, right there by inspection, 41 observances of the 26 to 30 range, so our mode is 28. And our pace, the 10-mile range containing most observances, looks to be the 41 and 38, so from 26 to 35 miles per hour, that's our pace. All right, so that's a quick look at speeds. All right. Let's move on to some trip generation. Trip generation. I'll read this, and then if I need to augment it, I'll do so. Traffic engineers prepare traffic impact studies. So traffic impact studies you frequently run into with a developer who wants to build in a certain location, and it's abutting, say, state highway. State's going to want to know, if you're going to be introducing so many trips, what's that impact going to be on the adjoining roadway? They're going to want you to do a traffic impact study. One of the key components of that traffic impact study is your trip generation. So we prepare traffic impact studies to assess the potential traffic impacts, new land development on the surrounding road network. Instrumental in this analysis, the forecasting and assignment of new vehicle trips associated with the development to the street system. Trip generation is typically estimated by applying trip generation rates. I belong to the Institute of Traffic Engineers. They have compiled study upon study and grouped them by land use type. You'll hear the term land use code, which is it's sort of like the Dewey Decimal System of land uses as it applies to trip generation. I'll show you an example in a moment here. Engineers give ITE their traffic studies, and over time you compile enough of these, you get enough studies, you can see trends in the data, and you can estimate trip rates depending on the size of the development, or if it's an office use, it could be it could be 1,000 square foot per 1,000 square foot. If it's a fast food restaurant. Fast food restaurant. I'm trying to remember the metric they used to compare with. As a sit-down restaurant would be number of seats. Fast food restaurant might be how many windows do you have, things like that. So all these variables are what's the word? Coefficient. Anyway, trip estimates may be based on a number of independent variables depending on land use. Examples from the Transportation Traffic Engineering Handbook are provided on the next 2 pages. More detailed information is contained in trip generation. Single page from trip generation all follows, which provides trip rates for the office space. We'll take a look at that. Estimated vehicle trips for development are assigned to the roadway network in accordance with an assumed trip distribution. The trip distribution may be derived by examining a variety of data. U.S. Census data. How many people are in this census block as opposed to that one. Market studies, existing traffic patterns, the like. So I thought I had, there it is. So yeah, here's an example, general office building. How many trip ends could be origin or destination per 1,000 square feet gross floor area on a weekday? And it tells us there were 78 studies contributing to this plot, and the average one is 199,000. Since this is for a weekday, the directional distribution, as you might imagine, half in, half out over the course of the day. If this were a trip generation table for AM peak, you might for an office building, you'd see more coming in, fewer going out, and the reverse in the evening. So this is saying the data that they found, there I want to go. So depending on the x-axis, the sizes of the various developments, and on the y-axis, the number of trips they recorded for these developments, plotted out, you see your trends. There is a fitted curve, a logarithmic curve, or a straight line average. Depending on what you call the R-squared value, the higher the R-squared value, the more likely you can go with the average trip. If it's a lower one, you'd be better served to use the logarithmic rate. And some other information they're giving here, range of rates. So the measurements they got, the rates they measured range from 3.58 trips per 1,000 to 28, and the standard deviation they measured is that. So what can we glean from this? Let's take a look at an example here. All right. Second while I get my notes up here. All right, assume a developer wants to construct a 250,000 square foot office building at the intersection of Main and Elm with a single driveway at Elm Street. Assume that the project traffic will follow the existing distribution shown. On the roadways you see percentages. Main Street, the southern leg is 30%, and then the northern approach 35%. And 20 and 15 on Elm. So assuming the project traffic will follow the existing distribution shown, how many vehicle trips per day will the project add to Elm Street west of Main Street? So Elm Street west of Main Street here. Excuse me. So knowing the existing distribution, we know it's going to add 20% of however many trips we calculate. So we've got a office building of 250,000 square feet. So, and we know from our plot here that it's per 1,000 square feet. So let's go back here. So we have 250 times average rate is 11 trips per 1,000 square feet, so 11.01, and that is 250 plus 2.5, so 2750 and change.
2752.
There we go. 2752. 20% of that going to Elm Street, so that's going to be about 550. It's going to be about 55.
550.
550. 550 of these estimated trips to the new office building are going to come to and from Elm Street. Okay. Now, just a comment on trips. That is, the way they're typically measured is that somebody is at the front door or all the doors of the building, of an existing building, and counting how many are going in. So depending on where it's situated and how people are getting there, are they getting there by automobile? Are they getting there by transit? Are they getting there by bike? They will often survey the people coming in and out of the building and try to determine mode split. So those 550 trips, they may not all be cars. They may be 70% cars. They may be 25% transit, and they may be 5% pedestrian or bicycle. So depending on the setting, you may have to, let's put it this way. If your concern is how many vehicles you're adding to the roadway, you may want to look into mode split to find out if all those trips are coming by car. If they're not, then you may be able to reduce the number of trips that you're that you're projected to add to the roadway. So, consideration to mode split. All right. Moving on. All right. Crash rates. This gets into our accident analysis and safety areas in the scope of the transportation depth exam. If you are dealing with a location, say an intersection, it's experiencing crashes, you want to not only know the number of the crashes, but you also want to have a metric that you can compare and contrast other intersections or stretches of roadway. So this is sort of this is a means to normalize, for the basis of comparison, crashes in various locations. So roadway segments, you typically report crashes per million vehicle miles. So going into that is the crash. So the output is the crash rate. The inputs are number of crashes over a given period. The time is the length of the period in years. The V is the average daily traffic, the ADT we spoke of earlier. And L is the length. How many, is it over a mile? Is it over 10 miles? If you're looking at intersections, you're more interested in number of vehicles coming in intersections, so the formula is slightly different. The output is, again, the crash rate for the intersection, but it's in terms of crashes per million entering vehicles. So you input the number of crashes, the time over which they've been collected, and the ADT. The volume is your ADT, or average daily traffic volume, coming into the intersection. Sometimes critical rate, that is, if I'm not mistaken, is the rate that you try to determine the critical rate so that you can know whether your intersection is above or below a critical value. So they try to establish the critical rate as a means for comparison among, for instance, here in Massachusetts, among the different districts. All right, so let's look at Oops, and we're going to go to a new. All right, so let's look at a crash rate problem. So we got a four-way signalized intersection, and it's experienced 26 crashes in a 3-year period. The peak hour traffic count has determined that 1,650 vehicles are entering the intersection in the peak hour. The K factor, again, the peak, the peak hour, the percentage of average daily traffic that is occurring in the peak hour is your K factor. The average crash rate for the four-way signalized intersection in this area is 89 crashes per million entering vehicles. So someone's looked statewide and they've determined that, or for this, for a large area, they've determined that the average rate is 0.89 crashes. The desired degree of confidence is 90%, so you want to know a couple of things. You want to know the crash rate, and is this crash rate critical? So let's make some calculations. All right, first we need the ADT, the average annual daily traffic of the intersection. So we know the peak hour volume, and we have a K factor that tells us how much of this volume, this is the percentage of traffic that has occurred in the peak hour. So how do we relate that 1,650 to the daily traffic? So that's just simply 1,650 divided by, again, that 9.2 is a percentage, so you want to divide it by 0.092. And that gets you an ADT of 17,935 vehicles. All right, so we've got our ADT. Let me bring this accident analysis. So we have our volume. Now we need to know the crash rate for the. Now we can calculate the crash rate for the intersection. So our A is the number of crashes, which we have as 26. Times that's right. I got to adjust this for since the rate is going to be expressed in million vehicles. A million entering vehicles. We have to factor this by a million, 10 to the 6th. And these 26 crashes occurred over a 3-year period. And we haven't, since we know we have a daily volume, we have to number of days, and then the number of vehicles here, 17,935. I think you'll find, as you're taking these tests, a lot of your calculations will come down to understanding the relationship of the units. So you've got your crashes here. That's just going to get deleted. Crashes, so you got million crashes, you got years converted to days, and vehicles per day, so the days cancel out, so you get vehicles, million per, crashes per million entering vehicles. You calculate that out, and you get 1.32 crashes per million entering vehicles. All right, now given that the average crash rate is 0.89, the question about is this crash rate critical it's a probability exercise, if you will. You apply this formula here, where you compare the critical crash rate and to the average crash rate. So, this should be, that's the question, is how does it relate to the, oh, I'm sorry, I shouldn't have said that. Critical crash rate. Right. So we will take the average crash rate and we will convert it to the critical crash rate. So let's see. So we were given the average crash rate for this area was 0.89. I'm just going to come right up in here with it. 0.89. And so K value checking my notes here, this looks a little off. That's that. Oh, you'll see this in the notes. If you look down here, it unfortunately uses the same letter as the peak hour factor, the K factor, relating peak hour volume to daily volume. So, in this case, the K is the level of confidence. We want 90% confidence per the given problem. So that's plus 1.282 square root of what is it, RA, which is the average crash rate for locations, which we were given as 0.89, times, let's see, the V, volume, same units as for crash rate. Yeah, I got to rework this one. Million vehicle miles, or MEV. 19.6. All right. There's a little. I'm going to kind of jump the shark here and go to the notes that you will see. There's an intermediate calculation that wasn't that I found out afterwards. Million entering vehicles. In terms, to get the input you need in terms of million entering vehicles, you have to convert the ADT with the length of the study converted to days. So it was you get your ADT times 3 times 365. That gives you 19.64 million entering vehicles. So that you're talking in the same terms as the crash rate that you calculated. So we have the 0.89 times the confidence, degree of confidence, times this calculation. Anyway, the critical crash rate comes out to be 1.19 crashes per million entering vehicles. The observed rate, 1.32, that we calculated here, is higher than the critical rate, and therefore the observed crash rate condition is critical. So it merits action be taken. All right. So, yes.
Where's the 10 to the power of 6 come from?
Yeah, I know. You're looking at it's really just a way to factor up. You could talk in terms of crashes per vehicle, and you'd end up with a fractional number, a low fractional number. So they basically boost it. It's the number of crashes per 1 million entering vehicles. So it's just a way to take that 1.32. Where is it? Yeah, 1.32 per million entering vehicles. If you didn't term it that way, it would be 1.32 times 10 to the minus 6 vehicles. So it's just a way to re-express, if you will, the number. All right. Let's see. Oh yeah, non-motorized. Non-motorized facilities. You can also get flow rates for bike paths if you're trying to measure the adoption of a bike path. You want to have some sort of metric to know what kind of flow rate you have. So if you're looking at the methodology applies to whatever vehicle you have on a public right of way. But this is in terms of bicycles, so let's take a look at this. An exclusive bikeway is operating with an average two-way flow of 20 bikes in the peak 15-minute period. The directional distribution is 60-40. Most nearly, what is the heaviest one-way density of flow at an average speed of 11.2 miles per hour? So density is volume over distance. So how do we, again, it's unit conversion really. How do we get to density of bicycles per mile? So we know how many bicycles we have, and we know the speed. So it's a matter of getting our units in order so we can convert. So our volume, we have. Let's see, where do I have it here? One second. Average two-way flows, 20 bikes in the peak 15-minute period. It doesn't match my notes here. What have I got? 11.2 miles per hour, bicycles per hour. Okay. 20 bikes in 6 races. One-way density of flow at an average. Okay. Yes. So our two-way flow is 20 bikes. So our directional distribution being 60-40, that means we've got times 0.60, we've got 12 in one direction, and that means we have 8 in the other direction. So here's our peak flow, 12 minutes in one direction in a 15-minute period. So that's going to give us 12 and 15 minutes is going to give us 48 per hour. So we've got a volume of 48 peak. I'm just going to 28 bikes in the peak direction per hour. And we have 11.2 miles per hour. Our hours cancel. And that'll give us 4.3 bikes per mile. Bikes per mile. B. All right. Let's move on to. I've included notes that just for let's call it education purposes. I don't have a specific example apart from. Come back here. This is a typical. I was trying to compile notes for safety. This is a typical collision diagram that we would include in a road safety audit, in which we've compiled crashes happening in an intersection, and we tried to categorize them by type of crash, rear end, head-on, angle, the vehicle types you see there. Are they left turns? Are they angle crashes? How severe were they? And if there's any information on the roadway surface. These are data points you'll get out of crash reports that you can get from your local police or the state police. All right. This section I've included here is it's about 50 pages of intersection capacity analysis. I'm going, so that I don't put you all to sleep, I'm going to just point out the methodology. Sorry, I'm going to come to stop that. Let's get my hand tool here. All right, let's talk about the methodology. When we're looking at intersection capacity, you can think of it in terms of an intersection right out here, Huntington Ave and Forsyth Street. You've got so many lanes, and you've got so much traffic trying to use it. You've got so much time allocated to the phases serving that intersection. So you want a level of service as a measure of it's a measure of delay per vehicle experienced, and the inputs into it are volume to capacity. Well, we'll go over here. So step one, determine movement in lane groups. So here on Huntington Ave, you've got 2 through lanes, but they also serve left turning vehicles and right turning vehicles. So you've got a left through lane and a through right lane. So you do your geometric analysis of the intersection, and you determine movement groups and lane groups. Movement group flow rate, how many vehicles coming through over time. Lane group flow rate, you adjust for saturation flow. If this were at saturation level, how much traffic could you expect to process? You look at how much is arriving during green, so that in theory they could get through as they arrive from the previous intersection. And then with these inputs, you can calculate your volume to capacity ratio, calculate your delay, and your delay is striated into levels from A to F, I think it's under 10 seconds is level A, and over 60 seconds is level F. So if a vehicle is, if your average vehicle is experiencing 30 seconds of delay, that's going to be somewhere in the middle. I think, so here's the step about movement groups and flow rates. You group by cars making the same movements. Group flow rate. This is why I don't want to put you all to sleep by looking at all the factors that can adjust the saturation flow rate. You start with a base and you adjust for lane width and heavy vehicles and grade. All the things you can think of that would impact flow through an intersection. You know, is that car too close to me? Well, that's the function of lane width. Is he turning? Well, he has to slow down. He's impacting the flow rate because he's slowing down the vehicles behind him. So there are all these factors that go into adjusting the saturation flow. And then there are tables in there for your adjustments. So the narrower lane, the smaller, you adjust down for the flow. If it's a wide lane, you adjust upward. I'll just kind of zip through these. You can go through these at your own. Proportion arriving during green, phase duration. There's useful diagramming of relating delay to arrival rates and discharge rates, and basically it's the measurement under the curve. Volume to capacity ratio, and then you find your critical lane groups, and then you determine your delays. Delay terms you'll commonly see: control delay, the delay due to the control of the intersection. Is it a signal control? Is it a stop sign control? Uniform delay, incremental delay, initial Q delay. Initial Q delay, the startup delay when you're stopped at a red light. All right. There are, of course, terms for formulas for determining the composite terms. And then, once you've calculated your delays, delay, interpretation of results, volume to capacity ratio. Oops, that's pedestrian space. I want my table. Where is it? Where's my LOS table? This is pedestrian service time. You can also come up with levels of service for your pedestrians. All right, pedestrian delay, LOS score. Determine LOS. Bicycle mode. All right. 1 second. Where's my LOS? Just trying to get to my LOS for cars. Pretty sure I put it here. Well, that's something I'll have to fix, is to put in the I'll make sure that the LOS table gets in there. All right. Let's get caught up with this. We'll get to an example. Signal length. All right. Capacity. Flow rate. Yeah. I reference as an exhibit that I neglected to include the LOS table. I'm sure if I looked it up fast I could find it for you, but LOS, so it's A through F. It's roughly in 10-second increments. 0 to 10 is A, 10 to 20 is B, 20 to 30 is C, etc. It might adjust somewhat, but I think that's generally it. So let's look at some intersection analysis. For instance, signal timing. When concurrent signal timing is provided, pedestrians and vehicles move in the same direction at the same time. Current practice now, you'll get what's called the leading pedestrian interval to give PEDs a head start. So you'll have your clearance, red clearance in the intersection, and then you'll get your walk phase to give the PEDs a head start, and then you'll get your concurrent green phase. So it will impact any right-turning vehicles, but PEDs will get across, and it's safer for the pedestrians. So minimum green time provided must be sufficient to accommodate pedestrian crossings, even if not all the time is needed to move vehicular traffic. So you may not have, you may not need, there may not be demand for the vehicles, the green time for the vehicles, but if you're getting a pedestrian across, they need to have enough time to get across the intersection. So minimum green time pedestrians, as you see there, identified by G sub P, 3.2 plus L being the width of the crossing, plus 0.27 times the number of pedestrians per cycle. So let's look at a sample there. Oops, come back here. All right. Main Street crosses 3rd Street. 3rd Street is 30 feet wide, so that's telling us that the crosswalk is 30 feet wide. 100 pedestrians per hour crossing 3rd Street. It's a two-phase signal, so basically a simple crossing north-south versus east-west. Signal cycle length is 70 seconds. So if it's 70 seconds, you would know that you'd have, let's see here, draw. 70 seconds, so we got 3,600 seconds in an hour divided by 70 seconds. Gives you roughly 51 cycles per hour. So let's take a look at what we're trying to determine here. Calculate the number of pedestrian crossings per cycle. Yeah, well, like, all right, yeah. I'm trying to, it's simple. Attached is simple. Determine the minimum green time for Main Street based on pedestrian crossings, yes. Green time. So the formula, as we see there, to calculate green time, we need to know the length and the number of PEDs per cycle. So number of PEDs per cycle, so we have 100 PEDs per hour. Convert the hour to, because we know how many PEDs per hour, we know how many seconds per cycle. So to get PEDs per cycle, we've got to do a little conversion. So 100 PEDs times 1 over 3,600 hours per second times 70 seconds per cycle will give us 1.94 PEDs per cycle. And how much green time do those 1.94 PEDs need? Well, they need 3.2 seconds plus 30 divided by the standard rate. Used to be 3.5 feet per second for pedestrians, but they've skewed it more recently in the most recent MUTCD to 4 feet per second for more to give those disadvantaged more time to cross. So 30-foot crossing at 4 feet per second is 7.5, and then modifying the number of PEDs per cycle times 0.27, and that says that your green time for your PEDs needs to be 11.2 seconds. So your pedestrian time is that green time isn't all say walk light time, you typically have in this area it's like a 7-second walk indication, and then you have your countdown indication, and then you have your clearance interval. So between your walk and don't walk, you're going to want to allow for at least 11.2 seconds for your pedestrians to get across, and then clearance time. Another example, determine the critical flow rate to capacity ratio, the overall VC ratio for the intersection. Assume that you've already calculated the following. 800 vehicles per hour on the east-west approach, and the saturation is 2103. The north-south approach, 667, and that saturation flow rate is 16.25. So critical flow rate to capacity ratio is defined as X over C, where X sub C equals Y sub C times the cycle over the cycle length minus the lost time. So it's a two-phase signal. You typically have you lose 4 seconds per phase when you change phases, clearance time, etc. So two-phase signal, you're going to lose 8 seconds. So cycle length, the cycle is 70 seconds, you lose 8 seconds, so you have 62 seconds to work with. And the Y over C is the sum of the two ratios, the east-west, which I believe was east-west was 800 over 2103, and the north-south was a flow rate of 667 over 1625. So that'll get you, the sum of the critical flows is 0.79 divided by 62 seconds. And so this is saying the intersection is at 89% of capacity. So it's getting close to jamming. All right. And last sample on this, looking at intersection capacity. Determine the intersection delay and level of service. Assume that you have already calculated these. So for each approach, you've got eastbound, westbound, northbound, southbound. You've got these delays: 59 seconds, 31 seconds, etc., and the flow rate for each approach. So basically, you're going to take again, it's going to be a weighted average of these delays over the through the whole intersection. So you're going to, it's going to be a measurement of the delay per vehicle, averaged out over the whole intersection. So we'll go right to the calculations. Weighted average delay for all lane groups. So calculate this. So you take, so it's the units here, it's seconds per vehicle. And times this rate multiplied out and then divided by the sum of the rates will give you your weighted average. So as you can see here, east, the four directions, their delays multiplied by their rates divided by the sum of the rates will get you 34 seconds per vehicle for the whole intersection. And in the LOS table, 34 seconds is LOSC. So that's a quick and dirty look at intersection capacity. Traffic control needs studies. This is where you come into your warrants. There are are when you, not every intersection necessarily warrants a signal light. There have been warrants developed that will quantify or categorize the intersection, and these metrics have over time have been used to through engineering studies indicate whether a traffic signal is warranted. So it doesn't guarantee that one will be, but it will strengthen your argument if you have, if the situations you have cross certain thresholds. So you can see the warrants that are listed. This comes from the MUTCD, the Manual on Uniform Traffic Control Devices. I think it's one of the references in the list, in the specifications. 8-hour vehicular volume. Let's go, wait. So you measure, let's see, here it is here. If your traffic measurements for major and minor volumes cross certain thresholds, then it would meet the warrant. 4-hour vehicular volume, it tweaks the relationship slightly. Intended to be applied with the volume of intersecting traffic is the principal reason to consider installing a traffic signal. Peak hour, you may have only you may have situations where you've just got the most volume in a peak hour. So those tables you saw earlier, they're also graphed here. If you're more visually oriented. Pedestrian volumes, if pedestrian volumes cross a threshold, you may be looking for a signal. If it's a school crossing, you may want something that you may activate during school hours. Coordinated system helps. If you want to maintain progression through a corridor, you may need to introduce a signal to keep the flow at the rate you want. Crash experience. If you have an unsignalized intersection that's experiencing a lot of crashes, that could be reduced or mitigated by a signal. That could be worthwhile. Roadway network. I've not run across this too often. Justifying concentration organizational traffic law on a roadway network. And then intersection near a grade crossing. You may need it if you need to protect or keep at a railroad grade crossing. You want to keep your cars from encroaching. So the MUTCD provides those tables for, basically they're the values that establish the curve that establish basically the thresholds for whether or not a signal may be warranted. So what goes into those obviously are a collection of your, in the cases of you collect your volume data, traffic volumes, pedestrian volumes, school crossings, etc. And with that, we can look at an example problem here. So in an urban location, two streets intersect. Neither street has a raised median island. 85th percentile in each street is 35 miles per hour. Both are two-lane, two-way streets. A is the major, B is the minor. Recent traffic count shows these volumes on each approach expressed in vehicles per hour. The signalization of the intersection warranted based on warrant 1 8-hour vehicular volume, condition A, minimum vehicular volume. So let's see if I can, let me just bring that table right up. On this side, take a warrant, undo that. Where's my pages? Tool. Where's my hand tool? All right. Warrant 1, 8-hour vehicular volume, condition A, minimum vehicular volume. So you can see some of the criteria you need: number of lanes, not my highlight, my draw tool, number of lanes, major, minor, vehicles per hour on the major street, total of both, vehicles per hour on the minor street. So you have your major street volumes, your minor street volumes, so you're going to want to sum those and then look at each sum and compare them to the tables here. And I'll cut right to the chase. We've got it right here. So you can see 100% criteria, 500 vehicles per hour for the major street, which is, I want to go back to this for a second. Neither is race. Both are 2-lane, 2-way streets. So you need to understand that when you 2-way street, you've got one approach in each direction, okay? So when the warrant table's number of lanes for moving traffic on each approach, so you've got the major street, 1 lane, minor street, 1 lane. So looking for the 100% on the major street, so we're looking at 500 as the threshold, and on the minor street, 150 vehicles as your threshold. So if we look at our totals here, sorry, I should have mentioned, for the minor street, for the major it's a sum. For the minor street, it's higher volume. As long as either of the approaches on the minor street hits the threshold, then it's warranted. So you look at your totals for the major street, and you can see that from 8 a.m. to 6 p.m. You've crossed the 500 vehicle threshold, and on the minor street you've hit the threshold in many of those hours, and on the right you can check off which hours have you met both. So 8 o'clock, 10, 11, 12, 1, 2 o'clock, 4 o'clock, 5 o'clock hours. Those are the hours in which you met both thresholds. So yes, you have met the warrant for a signal allocation. All right, now if the state of the art in traffic software codifies all this, and you input your volume data and it will do the comparisons for you, but still you want to have an understanding of what's going on in the black box. So here's when you're doing your warrant analysis, you have the 9 warrants, you have your data input, so as many of the conditions you want to try and see if the warrants are satisfied, you input that data. So you a moment ago, is the signal justified based on the 8-hour vehicular warrant condition A? You can also look at it for condition B. Condition B looks at the vehicles on the major street total of both approaches, and the number of vehicles on the minor street want a correction only. So this is the interruption continuous traffic. If you've got vehicles pulling out of the side road, that and maybe not as much. Well, vehicles coming out of the side road will interrupt your traffic flow on the main line. So if you've got you reach a threshold, you may need to look into putting up a signal. So for the interruption continuous traffic warrant, your criteria are 75 on the major street and 750 on the major street, 75 on the minor street. Higher threshold for the major street means that you don't meet it as often. You only meet it in the 8 o'clock, 12, 1 o'clock, and 4 o'clock hours here. On the minor street, where it's actually lower than the threshold for condition A, you're hitting it more often, but excuse me, you're only satisfying it in both conditions for the major and minor street at 8 o'clock, 12, 1 o'clock, and 4 o'clock. And the criteria says that it needs to be met. There are only 4 such hours you need, and you're not getting the required 8 hours. So that warrant is not satisfied. So that goes in your report. It's satisfied under condition A, it's not satisfied under condition B. All right, so that's a quick look at signal warrants. I've been talking for, an hour and a half straight. I'm going to grab a quick mouth of water. If anybody needs a break for anything, I'll be right back. And if nobody needs a break, I'll just pick it right up, but I don't have any water handy, so there you go. Should I turn this off? Or? Pause it. I hit the pause. No? Okay. Well, it's just that you're going to have me drinking.
Just a second. Yeah, no problem.
All right. I'll be right back. Okay, home stretch. Let's look at some traffic control here. This is an example of two-lane roads intersect at a 4-way intersection, as shown in illustration A. To reduce the number of vehicle conflict points at the intersection is replaced by this simple 1-lane roundabout shown in the illustration B. Most nearly, how many crossing and merging conflict points will be eliminated by replacing the intersection with a roundabout? This is one of the benefits of roundabout. Fewer conflict points means fewer crashes. Well, different types of crashes, but less exposure, let's put it that way. Because until the driver population gets used to it, where you instead of angle crashes, you may have rear end crashes. But you have rear end crashes at signals too, so hopefully it reduces the exposure, shall we say. So how many crossing and merging conflict points will be eliminated by replacing the intersection with a roundabout? Well, where do we have conflict points? It's a simple enumeration. So it's probably best to go at it systematically for approach by approach. So let's look at the northbound. You're going to, let's see if I can draw these well. You're going to have a conflict with the westbound left turners. You're going to have a conflict with the southbound traffic. You're going to have a conflict with the eastbound left turners, and you would have a conflict with merging traffic. So 1, 2, 3, 4. Northbound, conflict with the through traffic, conflict with the turning traffic. All right, so we got 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Go away. And 11. I think I got that right, but I gotta double check. Okay. Yeah. Right. Okay. Maybe that makes more sense. Let's just erase. Yeah, I'll get right and tight on that. Your conflict points. Yeah. Okay, conflict, 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 at both the crossing and the merging points. There. All right, so it's northbound, southbound, similarly, merge, cross, 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 merge, merge, cross, cross, merge, cross, merge, and then east, cross, cross, merge, and west, cross, 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 merge, cross, 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 merge, and cross, merge. So I think that's all of them. It's very symmetrical. Missed that one there. Come here, you. That one there. Oh, you're gonna do this to me? Yeah. Anyway, there's one in there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. 24 conflict points. A typical T, a typical cross. Where are your conflict points here? Merge, merge. Let's see, merge, 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 and merge. (24 minus 4), 20. See, shouldn't we have roundabouts everywhere? Less delay, less waiting at traffic, less waiting at signals. Anyway. You'll see that's in there in your notes. All right. When a traffic signal is put in flashing operation, which of the following statements is false? Yellow indication should be used for the major street, and a red indication should be used for all other approaches. Well, that's true. You only want to give right-of-way to one direction and withhold the right-of-way to a crossing one. think I'm just going to do process of elimination here. Each approach or separately controlled turn movement should be provided with a flashing display. Yes. You don't want to combine displays for, this comes back to lane groups. You don't want to have, say, your left turn having the same control as your through movement. Protected or protected permissive left turn movement should flash red when the through movement flashes yellow. Protected protected is you have the right of way and any conflicting movement does not. So you've got yellow, everybody else should have red. So permissive is when everybody potentially has the right of way, so then you have yield conditions. So protected or permissive left turn movements should flash red when the through movement flashes yellow. I think that should say the opposing through movement. Protected or permissive left turn movement should flash red when the through movement flashes yellow. Yes, because if someone has a permissive, which is a yellow indication, anything that opposes it you want to have as red. The most restrictive minor street should have a red indication, and all other approaches may have a yellow indication. That's too general. The most restrictive minor street should have red. You could have a less restrictive minor street, and you still want to have that as red because your major street most likely has yellow indication. So there's your falsehood. It's not in my notes here. If I can remember to do it, I'll add. There's a section from the MUTCD. If you have it, hopefully you have it in PDF form. You can get it from the FHWA website. You can download it. You can download the whole PDF. I carry the whole MUTCD on my iPad. You never know when you're going to need it. But there's a small section on signal indications. So if you're taking the transportation depth, it may be worth your while to look at the justification for signal protected and permissive indications. All right. To avoid possible moving conflict or collision, all signal faces should flash red, meaning all approaching traffic is to stop. Alternatively, flashing yellow can be used for major movement, and any non-conflicting turn moves that have adequate sight distance to proceed without coming to a full stop. It is unsafe to have more than one conflicting approach with yellow indication. All right. The depth on the specifications talk about. Let me go back to the safety section there. Oops, sorry, get that. Construction, roadside work zone. I don't have a specific example here, but I thought it was worth including. The components of a temporary traffic control zone, things I'm doing nearly on a daily basis are coming up with temporary traffic control plans to get around construction. So you need to know what kind of work you're trying to get around. What are the speeds of the roadway? Are you shifting it? Are you merging it? So these are the components of the work zone that you may have to design around. The advanced warning area, I'm going to go from bottom to top here. The advanced warning area tells traffic what to expect ahead. So you start with your road work ahead sign, and then a certain distance down the road, you tell it's all about managing driver expectation. You tell the driver what type of maneuver you're going to ask them to make. You know, is the shoulder closing? Do you need to shift a lane? Do you need to merge? If you are merging traffic, you need to give them, if you're merging traffic and they're going a certain speed, you need to give them a certain distance to do that. That's the transition area. Then there's the work area itself. If you want to protect your workers, you want to give them a buffer zone. How much buffer space you want to give them? Well, if you've got a vehicle potentially encroach upon it, you want that vehicle to be able to stop before they get to the buffer space. So typically it would be stopping sight distance. Then you have your workspace, and then you have your downstream taper, you're shifting back, and then you end your work zone. So these are the elements of a temporary traffic control. So what you'll often so there are tables dependent upon speed. You see the A, the B, and the C. I'm sorry, those aren't dependent on speed. Those are the series of signs. The C is what you typically encounter first as you're driving, the C sign. So it'll start out the sum of this distance. It'll be, so for instance, if road work ahead is a mile, road work 1 mile ahead, you're going to start that a mile back, and you'll have 2,640 feet to the B sign, which will be the type of maneuver you want them to make. And then the A sign is, let's see if we got an example of it here. Shifting taper, so let's see, you get your 3 signs, so there'll be a road work ahead, you'd have a shoulder closed, and then a shifting taper over here. There is a couple of formulas that are useful to know. Well, actually, these 2 tables are useful. They're typically featured in every MassDOT compilation of temporary traffic control plans. The merging taper. If you've got 2 lanes of traffic merging down to 1, you need to give them, L is the measure of the length that you typically need to give them. If you're having them merge, you need to give them the full length. If you're shifting, you're keeping the lanes so that they don't need time to merge, they just need time to adjust. So you only need half the typical length. And for shoulder taper, you just need 1/3 of the length that you, 1/3 of the taper length. And the formulas for calculating the taper length are there in table 6C4. If the road speed is 40 miles or less, then the length of the taper is WS squared over 60. W, the width of the lane you're shifting, or the offset as they call it here. S is the posted speed limit, or off-peak 85th percentile speed if it's not actually posted yet. But it's the posted speed limit in miles per hour. So you would have, so for a, you don't do any conversion, you don't do any, it's the speed expressed as feet, and then divide by 60. If it's a 45 miles per hour or more, it's just the length is the width times the width you're shifting times the speed. So for instance, on 93, there's a lot of work being done for a lighting. They're upgrading the lighting on 93 South, and They need to work in the median for the high masts. So they need to close the left 2 lanes. So they need to shift and merge traffic into the other, the remaining 2 southbound lanes. So you have to give them, since they're merging, you need the full length. So it's the posted speed on 93 up north is 65, and it's a 12-foot lane. So you need 780 feet for that taper, so that they'll have time to complete the merge. In theory, they could do it at speed if they were cooperative. If volume is such that you're going at a lesser speed, then you've got ample space, and people tend to pack up and then alternate. If it were, say, out here in Huntington Ave, and you needed to close a lane, well, you would have 12 feet for the lane. Your speed out here is 30, maybe 25. 30 squared, 900, and divided by 60, 900 divided by 60 is 15. So a rule of thumb, a 35 mile per hour speed zone, you're tapering at 1 to 15. So every foot you need to taper, you need 15 feet to develop it. So that's how that works out. So those are useful formulas that you could probably see in a question about work zone safety. And you can be sure the next time I do this, I will have an example worked out. Coming up on 9:20, and those are the examples I have worked out. I think that pretty much goes through what I was given at the outset. But I want you to get your money's worth, so if anybody has any questions or they want me to follow up on something, I'll be happy to call it back up. I will also, as I said, email you a link to this file so that you can stick it in your binder that you're preparing, along with your creative books or whatever you're taking, your resources. So I'll send you a link to the file, and you'll have that as a reference for working on the problems, practicing, whatever you have. Is there any questions I can? You'll have my contact information will be in the email as well. So that's all I got for you now. I hope you find it useful. I know it's going to be a bit of a blur. As you, now just to speak generally, I highly recommend you get your hand on a practice exam toward the end of your review, and if you can all arrange it, simulate the conditions, set aside a day and simulate the conditions and take the practice exam. You'll feel so much better going into the day of the exam. It'll feel familiar, and you'll have your notes on what you worked on in your example, and you'd be surprised how many of those examples are analogous to what you'll see in the test. So I highly recommend, do your drills, as you go along and work on a few problems, but toward the end, or even if you do it a 2-hour block and a 2-hour block and you take half the questions, half is better than none. So good luck. Thank you all. Thank you for coming, and thank you for not walking out. So, I take that as a small measure of success.